If you want to understand the mathematical machinery behind operator theory or quantum mechanics, you have to look at the structures that hold them together, Banach Algebras. This concept map breaks down how we get there. By the end of this, we are going to master 3 specific properties of these spaces: the Neumann series, the topology of invertibles, and the compactness of the spectrum. We start with a complete Banach space and introduce a vector multiplication rule. Specifically, the norm of x times y is less than or equal to the norm of x times the norm of y. We also define an identity element, E, where its norm equals exactly 1. This structure sets up a very practical problem. If you have an invertible mathematical object, like a matrix, and you introduce a tiny error or perturbation to it, does it break or does it stay invertible? Answering this is how we safely solve complex operator equations in the real world. We need mathematical proof that Meyer fluctuations won't cause the entire system to collapse. This brings us to Theorem 7.71. This theorem proves that if an element x has a norm strictly less than 1, the element e minus x is guaranteed to be invertible. On screen, you can see how this mirrors the standard scalar geometric series. To prove it, we construct a partial sum, Sn. Because the norm of x to the j power is less than or equal to the norm of x raised to the j, and our initial norm is less than 1, these subsequent terms shrink rapidly toward 0. Here is where the completeness of a Banach space does the heavy lifting. Because the space has no gaps, this Cauchy sequence of partial sums has to converge to a distinct limit, which we'll call S. When we multiply our original term, e minus x, by this converged sum S, the middle terms telescope and cancel out. As n approaches infinity, we are left with nothing but the identity, E. The strict completeness of Banach spaces provides a guarantee. We can construct exact algebraic inverses out of infinite series without worrying that the limit point might vanish. This leads directly to Theorem 7.7-2. This diagram illustrates a topological open set, G. If we pick an invertible point, x0, we can draw a specific protective radius around it, defined as 1 over the norm of the inverse of x0. If we take a perturbed element x inside that radius, we can factor out the inverse of x0 to create a new term, y. We then rewrite y as e minus c. The math strictly guarantees that the norm of z will be less than 1. We just proved what happens when a norm is less than 1. The term e minus c must be invertible. Because it is a factor of our original perturbed element, that invertibility cascades backward, proving x itself is also invertible. So let's test this logic. What condition on a scalar lambda would guarantee that the expression lambda times e minus x remains invertible when we factor out the lambda? By factoring out lambda, we get e minus x over lambda. For this to be invertible, the magnitude of lambda must be strictly greater than the norm of x. Here on the complex plane, any lambda outside this closed disk of radius norm x is perfectly safe. This gives us Theorem 7.73. All the non-invertible values, the spectrum of the element, are physically trapped inside this closed bounded boundary. A closed and bounded subset of the complex plane is compact, which means the spectrum is always compact. Some Banach algebras don't naturally have an identity element. To fix this, we pair the vector space A with the complex plane, creating an ordered pair, x and alpha. We assign the coordinate 0, 1, which acts as our new identity E, preserving the norm inequalities. These properties have direct applications. Because invertible elements exist in open sets with protective radii, we can confidently approximate massive matrices in early and modern computing. Look at the sheer scale of the ENIAC computer. When performing numerical linear algebra, systems rely on floating point approximations. Theorem 7.7-2 provides the mathematical guarantee that slight rounding errors won't suddenly flip a matrix from invertible to singular, crashing the simulation. We also see this in quantum mechanics, pioneered by mathematicians like John von Neumann. The physical, measurable states of a quantum system are directly defined by the compact spectrum of elements operating within a Banach algebra. Banach algebras give our equations topological armor. They allow us to translate abstract infinite series and geometric spaces into the concrete physical models and numerical computations we rely on today.